So, okay, back again. Today we're going to cover part 2 of the derivation process. Well, today we're going to do the reverse process, which is the SDXL inference. We need to derive some closed form solutions for some equations in the reverse process that give us an estimate for the variance and an estimate for the mean, because we're going to use that in the derivation of the objective function, and we're also going to use it just to perform inference for SDXL. So yeah, let's get started on that. I'm going to refer to my notes, especially towards the end of this, because there's some really dense algebra, which I'm actually not going to do all of it. I made a decision just thinking that it's a bit too, I just think it's a bit, it makes the video a bit too long and it's a bit unnecessary. I'm just going to show you, for instance, things like completing the square and stuff. I'm just going to describe the steps to actually solve it and show what we arrive at. I think it should be enough though. If you want to figure out the math on your own, you can use Wolfram Alpha or like ChatGPT or something. So, okay, let's get started. All right, so last time we found Q of xt given xt minus 1 I just learned I can do this, which is really cool, equals just Gaussian and then we did some more algebra and found this even more efficient closed form solution. Where alpha bar t and then of course that's that, and theta is equal to 1 minus alpha t. So okay, deriving so these are the steps we're going to do. First, we're going to show the marginal posterior is unsolvable. Then we're going to condition the posterior on x naught. Then we're going to approximate x naught because it's not something we actually have. And then we're going to derive beta t and mu xt. We're going to derive the variance and the mean, the estimated variance and the mean. Okay, so first, okay, so the marginal posterior, so the reverse process, so the forward process is x0 to xt, capital T, right? So it's corruption. So clearly the reverse, right, is inference. We're going from xt, pure noise, to an image, right? So the forward process is q of xt given what's before it. Because we established that it's a Markov chain by Markov property. So the reverse q of xt minus 1 given xt. So what is that? So this is the marginal posterior. Okay, this is proportional to q of x t given, so we're just going to do Bayes' rule. We have a normalizing constant, right? xt, but this doesn't matter because we already know that these are Gaussian. We already know the form of the posterior, right? So what's this? Q of x t minus 1 is q of x t minus 1 is the marginal, is a marginal distribution. So it's t minus 1. It's the joint xt minus 1 and x naught. Well, it's the marginal, right? So this is equal to, so we just use conditional probabilities. Oh. Right, so we have to marginalize over all possible x naughts in order to get the probability of xt minus 1, right? And so this is unknown. Therefore, q of x t minus 1 xt is unsolvable, right? If we knew the distribution of our data, right? I mean, that's what we're trying to find. That's why we're creating this model in the first place, is to figure out this data distribution. We don't know that, so this is an unsolvable integral. So So now what do we do? So we say, okay, well, what if we condition the posterior on x naught? Oh. What if we condition the posterior on x naught, and then use an approximation to x naught, right? To figure out what q of xt minus 1 is, to yield q of xt minus 1, right? So we say q of xt minus 1 given xt conditioned on xt and x naught, right, is equal to x naught. It's the joint. So this is just Bayes' rule. So x naught and xt. Okay. Okay, and then we're going to use conditional probabilities, right? So this is q of x. Well, let's do it. Let's say q of x, q of xt given xt minus 1, q of xt given xt minus 1, x naught, q of x t minus 1 given x naught, and then q of x naught. And then q of xt given x naught, q of x naught. So we're going to cancel these, right? And then we're going to say that this is q of xt by the Markov property, right? So we've already established in the last video that q of xt only depends on the previous time step, right? So this goes away. So now we have q of x t given xt minus 1, q of xt minus 1 given x naught, and this is q of xt. But now this is known and this is known as Gaussians. These are both known Gaussians, right? So that means that this can go away. That means that we can drop this because we know the form of the posterior. It's a Gaussian, so we don't need to normalize anymore because we already know it's a Gaussian. We already know it's a distribution. So we can say, therefore, q of x t minus 1 given xt and x naught is proportional to q of x t well, actually, we can say that it's equal to which is equal to, right, we've already established up here oh, okay. Oh. All right. Well, I don't want to do that. I'm just going to write it over. So we already established up there, or in the last video, that this is alpha t x t minus 1. These are the parameters times alpha bar, square root of alpha bar t x naught 1 minus alpha bar t times the identity matrix. And so now what we're going to do is we're going to multiply the two log PDFs, the log PDFs of these Gaussians. Okay. We'll just say this is step 2.1. So log PDF, look at my notes. So log PDF of a multivariate Gaussian parameterized by M and covariance matrix sigma is equal to D, which is the number of dimensions of your covariance matrix, log of the determinant of your covariance matrix plus the Mahalanobis distance which in our case, this is going to be the squared L2 norm because our covariance matrices are independent, so they're diagonal. So there's no dependency between the dimensions of our Gaussians. So we're gonna box this up. Let's just change the color of this. Let's change the color of this. So, okay. So I'm going to start looking at my notes here because this is where we just start to do a lot of algebra. So, okay, so the first, so we'll just call this A. The first Gaussian this is 1/2 xt transpose right. And so we're going to drop constants because we're looking, this is why we're looking at the log PDF. We're looking at the log because the log is going to cause the constants to drop, right? This is standard ML. This is why we like using log PDFs. And then we're going to say B This is why I'm looking at my notes because it's a lot of, it's very easy. It's very easy to make a tiny mistake here and then it's going to mess up the whole thing. So, okay. So now we're going to look at, right, log of A times B, right? We're going to look at log of this times this, right? That's the whole point of what we're trying to do, right? We have this, or we have this, and it's really the product of these two Gaussians. So we're going to look at the log product of those two PDFs. Okay, so now we want to do. These are the rules you're going to. I'm going to jump a couple of steps, but I'm going to show you the rules that you're going to use. I did this math already. You can walk through it. These are the rules you're going to use to solve it. M is a matrix. So X, Y, A, B are vectors. M is a matrix. Okay. And then if M is symmetric, then right. I should actually, let me do this. Yeah. Okay. So then if A and B are scalars, then A okay. So those are the rules you're going to use right here in this step, which is this equals plus alpha t x t minus 1 x t minus 1 transpose, x t minus 1, right? And plus 2 1 minus alpha t minus 1 1 transpose minus 2 alpha t minus 1 transpose x naught plus alpha t minus 1 x naught transpose x naught. Okay. So when we do the log of these, when we multiply together these two log PDFs and then we pull the log out, right? Essentially, we end up with this after doing some simplifications. And now, then we're going to use these rules here. Sorry. When we do the log of these two PDFs, or when we multiply the two log PDFs together and we use these rules, we do some simplifications and we end up with this, okay? And now, to get the new Gaussian, to get the form of the resulting Gaussian, we collect terms. We collect linear and quadratic terms and complete the square. I'm not going to do this, it takes too long. I'm just going to show you this is what you do, and what you end up with after you do quite a bit of algebra is covariance beta t 1 minus alpha t minus 1 minus alpha bar t we're going to define that to be, so this is beta, this is our estimate for beta t, and then the mean we're going to call mu post xt x naught xt plus alpha bar t minus 1 beta t 1 minus bar t x naught. Okay, we're going to call this 8.1. And then we'll okay, so now we go to step 3, which is we approximate x naught, right? Because we can see that we don't have this, obviously. This is what we're trying to get during inference. We're going from xt, we're going from pure noise to an image that we haven't seen yet, right? So what we're going to do cleverly is we're going to approximate this. We're going to use our UNet model we're going to reparameterize this as using epsilon, using the prediction of our UNet model, and then we're going to turn this into an approximate. And then we're going to substitute that in here, which is going to give us an estimated mean. And that's what we're going to use during inference. So we go back to our sampling form of a Gaussian that we covered in the last video, and we see that, right, xt is equal to right? This is what, that is the definition of this, This is the efficient closed form solution that we derive. Boom, boom. Okay, so we just write that out as the sampling form of Gaussian. And then we solve for x naught, which gives us, solve for x naught. That gives us okay, and then x naught, right? And then so then x naught hat, right? We just, instead of drawing from a standard normal, we draw from our prediction. We draw from our unit prediction, right? So we say the prediction for, so x naught hat is equal to which we haven't really covered this yet, but just know that this is what SDXL's unit is going to predict. It's going to give us a noise. It predicts the amount of noise that was, it predicts the amount of noise that was added to it predicts the amount of noise that was, right? So this equation Q of x t given x equals right, this shows us how we can go from x0 to xt in one jump, right? What UNet does is, so what UNet learns to do, what we train UNet to do, is predict exactly the amount of noise that was added to get us to this, right? So what we're predicting here is the amount of noise, the estimated amount of noise that was added to produce this theoretical x naught, right? It's the predicted amount of noise that was added for the number of time steps we have in between x naught and xt, right? That's going to give us x naught hat. Very clever. Very, very clever. So now we plug into and simplify. So we plug x naught hat into this. Actually, we plug it into there, we simplify, and we get So now we have, so therefore, now we have ut and the variance, the estimated variance. Estimated variance, the estimate for beta t. So therefore, right, we're trying to go from xt to xt minus 1, right? So now we know, right, we're just writing this as the sampling form of a Gaussian. Equals this plus, right, sigma, which sigma squared is beta estimate, so this is going to be this times c, right, where this is just so, yeah, now we're done. That's it. So let's do a review of this. So, okay. So last time we found the closed form solutions for the forward process, going from x0 to xt, corrupting the image, okay? Which we're gonna do during training. We're gonna sample a bunch of images for an epoch, and then we're gonna sample time steps to pair with the images. And we're gonna corrupt the images and make it using this equation to jump from x0 to exactly the time step. So we're gonna add exactly that amount of noise using the parameters for the Gaussian defined here, just knowing that the alpha bars and the betas are defined in this way. So these are the steps to deriving the reverse process. We're going to show the marginal posterior is unsolvable. Then we're going to condition the posterior on x naught, knowing that we're going to approximate x naught to get x hat, to get x naught hat, and then we're going to derive our estimated variance and our estimated mean. Okay. So showing the marginal posterior is unsolvable, right? So, you know, the forward process is this, so the reverse process is this, right? So what we're trying to find is q of xt minus 1 given xt. So we find the posterior using Bayes' rule. We remove the normalizing constant because we already know the likelihood and the prior are both Gaussians. So it's just the assumption we're making. It's the modeling assumption we're making. So what is this marginal distribution? When we expand it out, we find that we have this probability of the data, and we don't have this. That makes this integral unsolvable. So then we condition the posterior on x naught. We do some more math, and we find essentially that it's the product of these two Gaussians that we already know. We already know the form, right? So then we multiply the log PDFs of those multivariate Gaussians because it's always better to work with logs. That allows us to drop constants, and then we in turn products into sums. And so when we multiply, so the multiplication of those two log PDFs together equals this. Once we use these rules to simplify, then we need to group linear terms, group quadratic terms and constants, and then complete the square to get the new form of the Gaussian, which essentially will result in these two, after doing some algebra, it will result in these two parameters, this covariance and this mean, okay? And we finally define the estimate for beta t. Right, so yeah, this is the definition of the two parameters. So now still we don't have this value, right? So what we do is we know that we've been training our model to predict the amount of noise that was added from x naught to xt, right? So we know that our model gives a noise prediction of the exact amount of noise that was added. So we look at the sampling form of our Gaussian that comes from this equation. We solve for x naught, which gives us this, and and then we see this epsilon parameter, which is typically a standard normal, but we decide to use the prediction from our model that predicts the amount of noise added, which gives us x naught hat. We plug that back into here. We plug that in right here, and we simplify, and we get our prediction for mu. So now we have our estimated mean and our estimated variance for inference. Boom. So now that we have our estimated mean and variance for q of x t minus 1 given xt for that distribution, now we have all the building blocks that we need to actually derive the evidence lower bound for our objective function. So that's what we're going to do in the next video. So yeah, thanks for watching.